The topic of this video is Raspberry Pi in engineering systems, architectures, programming, and real-world applications in modern engineering practice. Intelligence is no longer confined to central servers or large industrial computers. Instead, it is increasingly distributed across engineering systems, embedded close to machines, infrastructure, and operations. In this context, Raspberry Pi has emerged as a strategically important engineering platform, particularly for embedded systems, cyber-physical systems, robotics, and automation, and especially within small and medium-sized engineering enterprises, SMEs. Raspberry Pi is not important because it replaces traditional engineering hardware such as PLCs, industrial PCs, or microcontrollers. Rather, it is important because it fills a critical gap between software-centric IT systems and hardware-centric engineering systems, enabling engineers to design intelligent, connected, and autonomous systems at low cost and with high flexibility. Raspberry Pi in the engineering systems landscape. From a systems engineering perspective, Raspberry Pi is best understood as an edge computing and intelligence node within a layered engineering architecture. Typical engineering system layers include physical processes, machines, robots, structures, environments. Real-time control, MCUs, PLCs, certified controllers. Edge intelligence and coordination, supervisory control and enterprise integration, cloud and high-performance computing. Raspberry Pi consistently occupies the edge intelligence and coordination layer, where it adds reasoning, perception, optimization, and integration capabilities without interfering with safety-critical control layers. This positioning is fundamental to its engineering value. Embedded engineering and cyber-physical systems, bridging software and physical engineering. Unlike traditional embedded microcontrollers, Raspberry Pi runs a full Linux operating system while still providing direct hardware interfaces such as GPIO, I2C, SPI, UART, USB, and camera interfaces. This allows engineers to develop cyber-physical systems in which software intelligence directly interacts with physical processes. In engineering terms, Raspberry Pi enables sensor data acquisition and fusion real-time, soft real-time, monitoring actuator coordination, non-safety critical, event-driven system behavior integration with higher-level optimization and analytics. This makes it ideal for engineering applications where adaptability and intelligence matter more than microsecond-level determinism. Programming and engineering toolchains, engineering-oriented programming environment. One of Raspberry Pi's strongest contributions to engineering is its programming ecosystem, which aligns closely with modern engineering workflows. Key elements include Linux-based operating systems for stability and networking, Python for rapid engineering development and AI integration, C++ for performance-critical engineering components, ROS and ROS2 for robotics and distributed engineering systems, OpenCV for engineering vision systems, MQTT, OPC UA, REST APIs for industrial communication, Docker for modular system deployment. From an engineering productivity perspective, this ecosystem dramatically reduces the gap between design, simulation, prototyping, and deployment. AI agents as engineering components, AI agents in engineering systems. In engineering contexts, AI agents are not abstract software entities. They are functional system components responsible for monitoring systems, state-making operational decisions, coordinating subsystems, triggering engineering actions, managing workflows and exceptions. Raspberry Pi is particularly well suited to hosting these agents because most engineering AI agents are orchestration and logic-driven, not computationally intensive. Importantly, the AI agent is software. Raspberry Pi is the physical host and execution platform. Together, they form an autonomous engineering subsystem. Robotics engineering applications. Raspberry Pi in robotic system architectures. In robotic engineering, Raspberry Pi is widely used as a perception and planning node, a ROS2 computation unit, a communication and coordination hub. Typical robotic architecture. Raspberry Pi handles vision, mapping, planning, and communication. Microcontrollers or PLCs handle motor control and safety interlocks. This division reflects best practice in robotics engineering and ensures both intelligence and reliability. Applications include Mobile inspection robots, service and logistics robots, construction site monitoring robots, research and pilot autonomous systems. Manufacturing and industrial engineering systems, intelligent augmentation of industrial control in manufacturing and industrial engineering. Raspberry Pi is used to augment, not replace, traditional automation. Common engineering uses include vision-based quality inspection, machine condition monitoring, predictive maintenance analytics, edge validation of digital twins, local optimization and scheduling support in these systems. PLCs retain authority over safety and deterministic control. Raspberry Pi provides intelligence, diagnostics, and adaptability. This hybrid approach aligns with modern industrial engineering principles. Construction, infrastructure, and fire engineering systems. In dynamic environments, construction and infrastructure engineering systems are often temporary, mobile, and highly variable. Raspberry Pi is particularly effective in these contexts due to its portability and flexibility. Engineering applications include structural health monitoring, environmental sensing, construction site safety monitoring, fire risk detection, and situational awareness. In fire engineering, Raspberry Pi supports Edge AI for smoke and flame detection, risk estimation and decision support, integration with simulation and modeling tools. Certified safety actions remain with approved systems. Raspberry Pi contributes engineering intelligence, not safety authority. Engineering systems for SMEs and small industries. Why Raspberry Pi is especially important for engineering SMEs. Small and medium-sized engineering businesses often lack large IT teams, capital for enterprise platforms, capacity for complex infrastructure. Raspberry Pi addresses these challenges by enabling low-cost, always-on engineering intelligence, on-premise automation and monitoring, incremental system deployment, one device per process architectures. For SMEs, Raspberry Pi often becomes the entry point to intelligent engineering systems, enabling automation, optimization, and data-driven decision-making that would otherwise be impractical. Business automation as an engineering problem. Business automation is frequently misunderstood as an IT problem. In reality, it is an engineering systems problem involving workflows, resources, constraints, and feedback. Raspberry Pi supports autonomous workflow agents, monitoring and exception handling, integration of digital and physical processes, continuous operation with low energy cost for engineering-driven SMEs. This translates into measurable productivity gains. Engineering limitations and correct usage. From an engineering standpoint, it is essential to recognize boundaries. Raspberry Pi is not a real-time safety controller, it is not a replacement for certified industrial hardware, it is not a system of record for regulated operations. Its strength lies in system integration and intelligence, not authority or certification. Conclusion: Raspberry Pi is a cornerstone of practical engineering intelligence. Raspberry Pi has become a cornerstone of modern engineering systems because it connects computation, intelligence, and physical systems in a practical and affordable way. It enables engineers to design and deploy intelligent, autonomous, and connected systems across robotics, industrial engineering, construction, fire engineering, and SME-focused applications. Its true importance lies not in competing with industrial controllers or cloud platforms, but in complementing them, accelerating innovation, and making advanced engineering solutions accessible in real-world settings. Final engineering takeaway: Raspberry Pi is important in engineering systems because it provides a practical edge intelligence layer that enables AI agents, embedded control, robotics, and automation to operate effectively within real-world, resource-constrained engineering environments, especially in SMEs and applied industrial contexts. If you enjoyed this discussion, don't forget to subscribe, like, and share. Stay tuned for more insights on AI, quantum computing, and emerging technologies shaping the future of software and humanity.